Hello, this is Stefan and I want to show you quickly the effect of the calibration in the DRS oscilloscope software. So let me first start the DRS oscilloscope. I have connected the evaluation board and you see here the channel 1 data after calibration. So let's go and measure the noise level. We have here the RMS measurement for channel 1 and this gives you here a mean of 0.4.5 millivolt. So let me go and turn off the calibration to see the effect of the calibration. I have here the primary calibration, which means the cell by cell offset, and here the secondary calibration, which does a readout calibration, which I will explain later, and removal of spikes. So let me turn this off, and now you see what you receive from an uncalibrated DRS4 chip. The mean here is about 7-8 millivolt RMS, and the peak-to-peak value, of course, is much more. It looks like 40 millivolt. Interesting fact now is that this noise pattern looks random, but it is only random because the DRS chain is always stopped randomly at an arbitrary position, and the readout starts from that position. And this is what's here on the configuration, rotate waveform relative to trigger, which is on. So if you turn this off, then the waveform shown here is always unrotated, meaning the leftmost sample is always the physical sample 0 in the DRS chip, and the rightmost is cell 1024 of the DRS chip. And as you can see, you have this pattern here, but it's stable now. And you also see a fact that the left half has a bit lower value and the right half has a higher value, and that's a feature of the DRS chip. You also see some spikes from time to time going down here, and this is because the first readout sample, the first and sometimes also the second readout sample of the DRS4 chip are unstable because the readout circuitry just stabilizes. So what you do is in the readout, you just throw away the first 1 or 2 samples and then you don't see these peaks. Now to do a calibration, you measure the contents of these cells, average over some 100 events. Make sure you do a robust averaging so that you have some spikes from time to time. These spikes should not be included in the average. So you do either a mean value or any other form of robust averaging. If you measure these offsets and subtract these offsets from the waveform, then you get this here. So you see the effect is dramatic. Noise went down to in the order of 0.9 millivolt. You still see the spikes here from time to time, but I can go and rotate the waveform back, meaning I show the waveform from the point where it's read out. So the first 2 readout bins are always at the left and they are clipped. So this is fine. What you now see is you see a little slope of the waveform going from up and then down here, and it's only a 1-2 millivolt effect. But you can also calibrate this slope, which has 2 effects. One is coming from the stabilization of the power supply on the evaluation board, and the second effect comes from the voltage leakage inside the sampling cells over time. So when you read out one channel, it takes some time, so the cells to the right have leaked more of their voltage and therefore they're a little bit lower. This is taken care of now by this secondary calibration. If you just measure this slope once and correct for this and you apply it, and then it becomes straight. And you see the mean now goes down to 0.5 millivolt of RMS. But now you see some spikes here, some positive spikes, and they are typically like 70 millivolts and they always come in pairs. So it's an effect from the chip. But it can be corrected for in software very easily because they're always in pair and they're always present in all channels. So if I enable here the second channel and put it below here, then and I go on the same scale here, 20 millivolt, then you see that they always go together with the other ones. So I can actually in software detect where the spikes are and remove them, and then they're also gone. And then you get a pretty nice waveform with a RMS below 0.5 millivolt. But the calibration somehow goes with temperature. So it's always important to keep an eye on the temperature, and when the temperature changes, you might need another calibration. So we are now at 48.4 degrees centigrade, and I just do another voltage calibration at this temperature, which has changed a little bit from the previous one. So the calibration goes on now, and as you see now with the new calibration, the noise goes down even a little bit further, 0.4, 0.43. So this is the effect of the cell calibration and of the readout calibration, and that's what you should expect if you do not do any calibration. Thank you for watching.